Good morning. I am Dr. G. Srinivasu, Associate Professor, Department of Mathematics, Institute of Aeronautical Engineering, Hyderabad. In this present video, I would like to discuss the problems in Module 3 of the question bank. The topic is partial differential equation solutions by using Lagrange's method. And I would like to solve these problems one by one. And see the first problem. Solve the partial differential equation mz minus ny into p plus nx minus lz of q is equal to ly minus mx. So here p means dou z by dou x, that is default, and q is equal to dou z by dou y. Now I will solve this problem by using Lagrange's method. So first I will write the reduction, the solution, the given equation, the given partial differential equation mz minus ny of p plus nx minus lz of q is equal to ly minus mx. This is the given partial differential equation where p is dou z by dou x and q is equal to dou z by dou y. Now I am writing the subsidiary equations. That is dx by p is equal to dy by q is equal to dz by r. Because the given equation is in the form pp plus qq is equal to r. This is small p, this is capital P, this is small q and this is capital Q and this is capital R, where p, q, r are functions of x, y and z. Where p, q are functions of x, y, z, then we can apply the Lagrange's method. The given equation is in the format pp plus qq is equal to r, where then the subsidiary equations are the dx by p is equal to dy by q is equal to dz by r. That is dx by, what is p here? Here p, what is p? Here p is mz minus ny, pp plus qq, what is q? nx minus lz. And what is r? R is the right hand side function, that is ly minus mx. Now dx by p, what is p? mz minus ny, and dy by q, that is nx minus lz, is equal to dz by ly minus mx, and call this is equation number 1. Now I would like to solve the equations by considering the first two fractions or second two fractions or first and last, or I can consider equal ratio also. So in this case I will use the Lagrange's method of multipliers, because here I will write it is mz, this is mz. The equation I will write here dx by, what is mz minus ny, mz minus ny is equal to dy by, what is the factor? nx minus lz, and is equal to dz by ly minus mx, And in this case, to solve this equation, it cannot be variable separable form like that. Then I can go for the Lagrange's method of multipliers. Now by multiplying the denominator and numerator, here with L and L, and here with M and M, and here with N and N. Then what will be in the denominator on adding each ratio I can write, each ratio is equal to L dx. I am multiplying the first factor, numerator and denominator with L dx. Here I am multiplying with M and in the denominator also M dy plus N dz by L into mz minus ny plus N Lm. M means nx minus lz, nx minus lz plus n into ly minus mx. Here the denominator, clearly this denominator is, what is denominator here? The lmz minus lny plus mnx minus lmz plus NLY minus NMX. So this, you see this value, LMZ gets cancelled, LNY or NLY both are cancelled, MNX will get cancelled, the value is equal to 0. That means what is in this method is we have to choose the multipliers, Lagrange's multipliers, in such a way that the denominator is equal to 0. So here I am choosing the multipliers L, M, N, and this is to be multiplied for each factor in the numerator and denominator. So after getting cancellation, the fractions remain same. So each ratio is equal to LDX plus MDY plus NDZ. Here n multiplied, here also n. So this is LMZ, this value 0. So what I can write it is on equating LDX plus MDY plus NDZ is equal to 0. So on integrating integral LDX plus integral MDY plus integral NDZ is equal to C1. C1 is the arbitrary constant. Or I can write it as L constant integral dx x, M constant integral dy y, N constant integral dz z, that is equal to C1, and this is the first solution, first independent solution of the given partial differential equation, and call this is equation number 2. So just I will explain. After writing the subsidiary equations dx by this one, dy by this one, dz by this one, we have to take any two fractions, first and second, or second and third, or third and first, whatever you can take. But here it is not possible to get the solution using that method. So that I am taking the Lagrange's multipliers, that is L, M, N. So I am using the Lagrange's multipliers L, M, N. The each ratio is equal to LDX plus MDY plus NDZ by L into MZ minus NY plus M into NX minus LZ plus M into LY minus MX. So that the denominator will be 0. Now this value on equating to this 0 into something, this entire 0. So LDX plus MDY plus NDZ is equal to 0. And integrating you will get the first independent solution. Similarly, I will use the, again I will write dx by the same equation number 1, mz minus ny. Mz minus ny, and dy by something is equal to dz by something. What is dy by nx minus lz? Nx minus lz, and this is ly minus mx. Ly minus mx. Now in the second set of multiplicating factors, I am using x, y, z as multiplicating factors. I am taking the multipliers. The Lagrange multipliers I am taking as in the second set as x comma y comma z. So that each ratio is equal to x dx plus y dy plus z dz by x into mz minus ny plus y into nx minus lz plus z into ly minus mx. So you can observe that the denominator xmz and mzx, these two will get cancelled, 0. nxy and nxy plus nxy minus nxy, those two gets cancelled. Similarly, minus lzy plus lzy, clearly all the terms will get cancelled and the denominator is 0. So that what we will get? Therefore, x dx plus y dy plus z dz is equal to 0. So I am taking integration. I am integrating integral x dx plus integral y dy plus integral z dz is equal to C2. Or what I can write simplified notation x square plus y square plus z square is equal to C2 dash, that is equation number 3. This is the second independent solution. The first independent solution is Lx plus My plus Nz is equal to C1. Second independent solution x square plus y square plus z square is equal to C2 dash. Therefore, the general solution is given by f of c1 comma c2 is equal to 0. That is f of lx plus my plus nz comma x square plus y square plus z square is equal to 0, which is the required solution of the partial differential equation. Right? So this is the essay type question. Similarly, see the second problem. Solve the partial differential equation px square plus qy square is equal to z into x plus y. So this also can be solved by using the Lagrange's equation because it is in the form small p into capital P is equal to small q into capital Q is equal to r, where p, q, r are functions of x and y and z. So clearly this is a Lagrange's equation. Here what is capital P? Here capital P is x square. What is capital Q? Y square. And what is capital R? Z into x plus y. So because it is a Lagrange's equation, the subsidiary equations is dx by p is equal to dy by q is equal to dz by r. That is dx by x square is equal to dy by y square is equal to dz by z into x plus y. Call this is equation number 1. As we have done in the previous problem, same method of solution. Then on taking first two, here I will write on taking first two. What are first two? Dx by x square is equal to dy by y square. Clearly you can observe that it is in variable separable form. X variables on dx side, y variables on dy side. On taking integration, on integrating, integral dx by x square is equal to integral dy by y square plus c1. So what is the integration? Integral x power minus 2 dx, x power minus 2 plus 1 by minus 2 plus 1, x power minus 1 by 1 or minus 1 by x. So the integration minus 1 by x is equal to, this is minus 1 by y plus c1. Or what is the first solution? 1 by y minus 1 by x. 1 by y. On writing left hand side, minus 1 by y will get in the form of 1 by y. Minus 1 by x remains same is equal to c1. And this is the first independent solution. Very simple. Dx by x square is equal to dy by y square. Already it is in variable separable form. Just on taking integration, you will get the solution. In the second consideration, it is not possible to take first and second. I can rewrite. From equation 1 I can write, from equation 1, dx by x is equal to dy by y is equal to dz by z by x plus y. Am I right or not? Dx by x square, I am writing dx by x by x. dy by y square, dy by y by y. Similarly, dz by z by x plus y. Now I will choose the integral multipliers, Lagrange's multipliers. On taking the factors 1, 1, minus 1. Now take Lagrange multipliers as 1 comma 1 comma minus 1. Then the denominator will be 0 or not. Then each ratio is equal to dx by x plus dy by y minus dz by z. I am multiplying 1, 1 and minus 1. So dx by x plus dy by y minus dz by z is equal to x plus y minus of x plus y. So clearly you can observe that the denominator is 0. Therefore what we will get? Dx by x plus dy by y minus dz by z is equal to 0. So integrating dx by x plus integral dy by y minus integral dz by z is equal to C1. Or I can put log also, because all are getting log. Log x plus log y minus log z is equal to log C1. Or what I can write on the left hand side? Log xy by z is equal to log C1. Or what is the value? xy by z is equal to C1. This is the second independent solution. What is the first independent solution? 1 by y minus 1 by x is equal to C1. Second independent solution, xy by z is equal to log C1. Therefore, the general solution, capital F of C1 means 1 by y minus 1 by x, and it is xy by z is equal to 0, and which is the required solution of the given partial differential equation. Here also we have chosen the multiplying factors for as 1 comma 1 comma minus 1, and for the first solution, on taking first two, it become variable separable form, and integrating will get the required solution. So see the problem number 3. Solve the partial differential equation p minus x square is equal to y square plus q. Solution. The given PD, the given partial differential equation, p minus q is equal to y square plus x square. Because we have to write first in the form pp plus q is equal to r. It is also Lagrange's type equation. Here, capital P is equal to 1, and capital Q is minus 1, and capital R is x square plus y square. Capital R is x square plus y square. Then, the subsidiary equation is dx by p is equal to dy by q is equal to dz by r. Or what I can write, dx by 1 is equal to dy by minus 1 is equal to dz by x square plus y square. On taking first two, call this is equation 1. On taking first two, dx by 1 is equal to dy by minus 1. Am I right? The first two equations, dx by 1 is equal to dy by minus 1. And integrating, integral dx plus integral dy is equal to C1. Or x plus y is equal to C1. This is the first independent solution. X plus y is equal to C1. And to find the second solution, I take the first and third relations, that is a d. On taking first and last, that is dx by 1 is equal to dz by, what is the last one? X square plus y square. Dz by x square plus y square. So here, from the equation number 2, y is equal to C1 minus x. From 2, y is equal to C1 minus x. And substituting, dx is equal to dz by x square plus C1 minus x whole square. Now, on separating x square plus C1 minus x whole square of dx is equal to dz. Clearly, it is in variable separable form. On integrating, integral x square plus C1 minus x whole square of dx is equal to integral dz plus C2. Integral dz plus C2. What is the integration? X square dx integration. X cube by 3. C1 minus x whole square dx. C1 minus x whole cube by minus 3. By 3 actually, and differentiating C1 0, x derivative 1 minus 1. is equal to Z plus C2. Or what you can write x cubed by 3 plus C1 means what? X plus y minus x whole cube by minus 3 minus Z is equal to C2. Or what I can write? X cubed by 3 and minus y cubed by 3 minus Z is equal to C2. That is the second independent solution of the given partial differential equation. Therefore, the general solution is given by, what is the formula? Capital F of C1 comma C2 is equal to 0. That is F of, what is the first solution? X plus y is equal to C1. So that is X plus y. First solution X plus y. Second solution X cubed by 3 minus y cubed by 3 minus Z is equal to 0, which is the required general solution of the given partial differential equation. So these are the all the problems comes under the Lagrange's method of multipliers or Lagrange's method by grouping. So both are possible depending on the given equation. So with these few problems I conclude my session, and thank you very much. And here I have taken the reference as a question bank of the course, Differential Equations and Vector Calculus of BT 23. That is regulations published by the Institute of Aeronautical Engineering. That is, thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.